Okay. I know some of the websites, your Blackboard, once in a while I refer the course material to this website. You probably noticed that. So this is scicecure.org. There, for this class, IASP 505, the last 3 text chapters are linked to this place. So you can check out operating systems in Python and network socket programming in Python, and also database management in Python. So for the rest of this class, the textbooks are available here. Okay. So if you click, for example, this, then you can get the text. There's one thing that I want to share with you. So that is this. Okay. So what we will do today, we'll finish up operating systems. We started the second half of the last class, but we will finish this the subject today, and then next 2 classes will be discussing about database systems. Okay, I know some of the database systems you've already tasted from your homework assignments, right, as I gave to you. So some of the Python statements can include database language, so-called structured query language. We call that SQL. Very, very simple SQL statements has been embedded in our small Python program. And of course, there in your projects, you need to be you need to highlight the data retrieved from your database, right? But all details will be discussed. Yeah, that is SQLite database. Okay. So to finish up operating systems, this is a slide that I prepared. So let's run it. Okay. Operating system structures. Multi-programming is available. Okay. In most recent operating systems, and also time sharing. So multi-programming, then we run several programs. One program may be running up front, in front, foreground, and many other programs that may be able to run a background, so that batch system is possible. So single user cannot keep CPU or I/O devices busy at all times. So multi-programming organizes jobs. For example, the program code itself, and then data that needs to be manipulated by that code. Together, code and data should be handled. And subset of total jobs in a system is kept in memory. If you want to run multiple programs in a single operating systems, then those all multiple program source code, it's not necessarily source code, but executable code plus data that you want to manipulate should be on memory. So everything should be kept in memory. So one job selected at one time, and then another job. Job in this case means a program. Program is program, jobs, file. They're all the same objects, but called differently. As a programmer, if you make some Python program, then that is a file. If you run it on, if you execute it, therefore, if it is running, then it is called a job. Job in operating systems perspectives. So operating systems can handle multiple jobs, meaning multiple programs, meaning multiple software files. So each file, each program, each job may need to handle data sets. Then both code and data sets should be kept in memory. If you have 10 programs to run, then all should be in memory. But if it is a single CPU, then CPU picks up one program at a time, while all others are still available. It's not necessarily one program should be complete and then another program then can be picked up. It is not the case. If it is the case, then that is a sequential execution program operating systems. But these days, many cases they don't do that, right? They make it concurrently. So a piece of one program runs while waiting for here. Right. Here I/O device. We have I/O device, and then CPU. CPU runs so fast, right? And I/O, it takes longer. Therefore, all the code and data should be kept in memory. So distance between memory and CPU is shorter than memory to the real physical storage. This is called I/O, right? This is I/O device. I/O takes a lot longer. It runs so slowly than this is CPU time. So all the code and data should be available in memory. Therefore, CPU can pick one code very fast, and if that code needs to data, then push it to back end, and put another program, another piece of another program, and handle it concurrently. So everything can be done efficiently here. So efficiency is important. right? In order to do that, there is one management, one software packages that handles jobs. We call that job scheduling. So job scheduling is one of the very, very important the functions of operating systems. Because operating systems need to handle multiple jobs, multiple programs, multiple software packages more efficiently. If efficiency is not really matter, then they can do one at a time. Hey, line up. I'll serve you one at a time. Doesn't matter, you wait longer. I'm okay, I'm the king. Then that is okay, right?
But it is no priority.
There's another issue. Yeah, priority can be done, job priority, if there is a too long, too much delay jobs, then you can increase the priority. Okay, that is also possible. All such things can be very simply and quickly implemented if you take data structures course. There's a priority queue programs available. Okay, so job scheduling is one of very important functions. As jobs are under scheduling, therefore some job needs to wait, right? While others are being handled. And some jobs needs to be terminated for many reasons, right? Because it is complete, then terminates. Or from external interrupt. Sometimes you can interrupt it, right? Before it is complete, you can terminate it. Many ways. So that those all needs to be handled by operating systems. Okay. Another one is time sharing, so-called multitasking. This is a logical extension. So CPU switches jobs so frequently, users can interact with each job while it is running. So this is interactive computing. Resources is limited. Okay. With the limited resource, if you have a very nice and very efficient operating system functions, then it can handle more jobs that one single system is supposed to solve. How? You do the time sharing, right? For example, this classroom, if you want to maximize and utilize the purpose of this room, then we do time sharing, right? As we did, right? We have this class at this time, and then right after this class, maybe another class can come in, okay? And if that is a little bit sequence, but the real time sharing is the following. We do lecture here, and the lab maybe another classroom, because another classroom has a lab for facilities. This classroom is for lecture only. Then if we hold two spaces for this single class, then no one can use, right? So we use this classroom half and move to the lab. And meanwhile, another class can come in to start early. That is concurrent, that is time sharing. If you think that logically in the real world situation, that is also handled and manipulated and implemented here in operating systems. Okay, what operating systems can be improved is the way that if you think, oh, in the real world, this could resolve more efficiently some problems, then we can implement it and adapt it to our operating systems. That is the case. Each user has at least one program executing in memory. Another we call here job, but if it is really in memory, then we call that process, memory, and if it is being processed, then we call that process. So process, job, or file, or program, they're all the same. But we call it differently depending upon where that object is available. If it is available in memory, then we call it process. Okay, memory or in CPU. So to do time sharing, your operating system needs to hold one piece of code at any single time. So swapping is needed if it is incomplete, so that you push that program back and another program into upfront to be handled, then swapping is needed. Swapping can occur in many levels. The physical levels of swapping is that any program that is big, not enough to fit in the current memory space, then your operating system look at the memory space and make a room to adapt to the new incoming process. Then all the memory should be written back to the permanent storage. That is also swapping. So swapping is the concept that can be applied to many different levels. Virtual memory. So memory space is another big issue in many cases. So that not only the physical, the core memory, and we may be able to think of the virtual memory. So part of the other resources can be used as a memory. So directly linked to that memory space, which is virtual memory. Virtual memory is accessory to the real memory. So we have a real memory and CPU memory, and then virtual memory. Why we need a virtual memory? To increase efficiency. Why? Because any programs, any softwares, any data, if they need to be executed, they should be kept in memory, so the CPU can access it quick. CPU doesn't handle anything that is currently in the hardware storages. If they do that, then your computer goes slowly.
So virtual memory is a temporary?
Virtual memory, sometimes it could be your hard disk drive. Part of your hard disk drive can be used as a virtual memory. So that is similar to the memory. Temporary means if it is persistent. No, it is not persistent. In that way, that is a temporary. Okay. So if you see the memory, okay, this is structure of a memory. Assume that if you have a 520 mega big memory space, then the first few spaces holds operating systems, which is the code, operating system code stays at that level. And then you have another program to be executed, so it should be loaded in your memory. So This is the first program. And another program, another program. Program can be in your memory. If you click on one of the icon, okay? If you click on Microsoft Word, then Microsoft Word is a job 1. So Microsoft Word itself is a code. But if you have a real file, say resume, then resume is a data, right? Resume is a data that is handled by Microsoft Word. And also you have another data that can be handled by the same code. It may be called resume 2, right? And then another program comes so that you run now Python homework 3. Then Python homework 3 is another job. So source code is a code. If your Python homework 3 handles some data, for example, HTML file, then that is the data, right? The data also should be in this, but a little different structure. But this is broad scheme. What this slide explains to you is that operating system code sits in memory, and any jobs that you want to handle, then that should be in the memory. Sometimes your memory is full, therefore no additional jobs can be considered, then your operating systems may complain to you, right? Insufficient memory, for example. You probably had that error sometimes. Then how can you handle it? You can close a couple of programs that you open, right? Then you will have space. At worst case, your operating system does not handle the jobs and schedulings, therefore does not understand that even if you close some of the jobs, your operating systems assume that it's still full, then your solution is very, very, there's some other solutions, but one of the solutions is that you need to reboot your operating systems. Then your operating systems at first has only operating systems in memory, right? These operating systems can be, if you turn on your system switch, power switch, then bootstrips brings operating system in your memory, first part of your memory, right? Then bootstrip doesn't not need to do anything. This is in EPROM, or this is actually in ROM, read-only memory. And this is RAM. Whatever your memory, these days you might have 8 gig memory, right? 8 gigabyte memory. That they are all RAM size. So after that, operating systems handles additional jobs. Okay. Interrupt. We learned interrupt last week. There are 2 types of interrupts available: hardware interrupt and software interrupt. Interrupt, one of the interrupt is that, for example, if it is a software interrupt, then in your program, there may be some exceptions and trap that is supposed to be handled. In your program, in your Python, then there's except, right? Try exception. If something happens, then try first. If there is an error, then it goes to exception. So whatever you say in the exception block should be handled. That is the type of interrupt. Hard interrupt is that you can interrupt this program by the three keyboard, right? What is it? If you're running on Windows systems, how do you interrupt your program? Control, Alt, and Delete, right? If you press the three buttons at the same time, then that interrupts your program, so that you can do some additionals, right? If you're running on Linux operating systems, then Control C. C for that, in that case, interrupt or cancel. So your operating systems, in normal cases, handles jobs, process according to job scheduling algorithm. You can change it, job scheduling algorithms, if you do system developer procedures. As Peter said, priority, if you want to do priority-based job scheduling, that is also possible. Then how do you know which one's higher priority than others? In what sense? That should be defined, right? And also implemented. By looking at the source code, if it is a very long source code, then let's say if you have two jobs coming together, by looking at the size of the source, if it is a longer source, sounds like long, it needs more resources, but not really necessarily, right? But anyway, by looking at some factor from the source code, if it takes longer, then you need to decide the longer process should be higher priority, or because it holds your CPU longer, you lower the priority. It is all up to your policy. Operating systems has also dual mode. Almost all operating systems has a dual mode. What kind of dual mode? It has user mode and kernel mode. Literally, as you see here, this is what user can use. But there is the very core level of operating systems, not normally allowed user to access. So kernel mode handles more significant jobs. So casual users cannot do anything on that kernel mode. So there is a mode bit provided by hardware. So it provides ability to distinguish when the system is running user code and kernel code. Some instructions are designated as privileged only executable in kernel mode. System call changes mode to kernel, return from all resets it to user mode, right? So two tiered of operating system mode. The significant and high privileged instructions needs to be sitting in that kernel mode. Increasingly, CPU supports multi-mode operations. So virtual machine manager. It's a VMware that is also available. So transitions user mode and kernel mode. See here, in your programs, so you develop one program, like Python programs. Part of this, where there is a external device is needed, for example, print. Then in user process, there's two types of process, right? So there is a user the mode bit, 1 or 0. So depending upon this, and if some of the programs needs system calls, okay, so system procedures, this is one of the programs that is only available here in the kernel mode. If that is needed, then it requests to the kernel mode, okay. It's not handled by your program. It's handled by operating system itself. In your program, you simply say print. You can print on your local monitor, or you can print it on the remote monitor, or you can print it on somewhere remote storage, whatever, right? So depending upon the hardness and significancy, it calls the system calls, and then this user mode don't do anything but switch that to the kernel mode. If it comes in this kernel mode, then this is a higher privilege execution, high privileges, okay, high power, superpower. If you are a hacker and attack this system, then you can, see here, there is some trap, right? This system calls. From user mode to kernel mode, there's a system calls. So you can have a free ride here. Then you can come to the kernel mode. And when you are in this kernel mode, you can interrupt that execution. Then it doesn't go back to the user mode if you interrupt this process. Therefore, you are here. If you are here, then what happens? If you are here, then you have a superpower. Because you have a superpower, and system is a whole. So you could do something, very powerful things. But anyway, in this, so that explains this. Timer is set to interrupt the computer after some time period. Keep a counter that is decremented by the physical clock. So there's a time settings, right? Operating system set the counter. When the counter 0, generate an interrupt. When it comes to 0, then the interrupt comes, so that it definitely go back to the user mode. So some significant, some instructions that needs a superpower, then it coming to kernel mode. But because this is dangerous, if somebody holds the privileges that is available in kernel mode, then your system is not your system. It will be the hackers. So your system try to handle, use some counter and push it back to the user mode. Of course, that is normal procedures. Process management. When your program, when your job, when your file is loaded in memory and picked up by CPU, then it is called a process. So process needs to be handled by your operating systems. Process is a program in execution. It is a unit of work within the system. Program is a passive entity, A program is a passive entity, process is an active entity. What does that mean? Program and process, they are the same objects, right? We're talking about same piece of program and process. Same guy. But if that guy is in memory, so that if it is actively working, executing, it is called the active entity. If it isn't, for example, in your hard storage, then that is a passive. It doesn't do anything, right? Thing is this, if you have a virus program stored on your hard disk drive, that is a passive entity. Although you have a very, very malicious virus on your hard disk drive, still okay as far as it keeps passive. Therefore, to destroy your program, the virus program, malicious program, is activated by, it is ignited by some of the small triggering program. It watch system clock, and when it comes to a certain time when it is set, for example, birth date of Michelangelo's birth date, then it ignites that virus programs. So about 20 or 30 years ago, I think 30 years ago, right? There's a Michelangelo virus available. That type of program is called Trojan, right? Trojan, the virus program, is hidden inside another program or hidden in the space anyway. So during some time, it is simply a file. It's not really well recognized. And at war time, it comes up and do some bad things. Okay, that is a Trojan. So Trojan is possible. Processor needs resources to accomplish its task. So processor stores as a file, and through I/O, input at I/O process, it loaded in memory. Once it is in memory, then it may be handled by CPU. And in CPU, it may bring data, so this process can handle the data. All right? This is very nice procedures. Processor termination requires a reclaim of any reusable resources. Single-threaded process is has one program counter. Single threading. But there may be multi-threading process also. Multi-threading process means multi-threaded program. If you code your program for multi-processing, then it is handled by this multi-processing, multi-threading. Remember that last time I was talking about multi-threading? For what? Yeah, socket programs, sniffering program. Then one big piece of a program needs to connect to the network and grab one packet and unpack it, and then identify each bits and bytes of that packet, and then we need to understand what that packet is. That is a long process. But the situation is that packets comes in continually, even way before I complete with the one packet analysis. I already have multiple packets comes in. Then there may be a lot of big bottles, right? Therefore, we need to create another thread. So when I receive one packet, and then I send it to another thread. Hey, you handle unpack it. That guy create another thread. Hey, you identify what each bits and bytes means. All such things, right? So concurrently, multi-threads can handle each different things, but that can be done in one single programs, but now divided into multi-threading, which is so efficient. That's what we say here, right? Here, if it's a single thread, then it is sequentially, means one at a time. If it is a multi-threaded, then program counter is available per threads. So if you have 4 threads, for example, then you have 4 program counters. Here single thread is, you have only 1 program counter, no matter what. In this case, multi-threading, you can create more and more program counter. Typically, system has many processes, some operating systems running concurrently on 1 or more CPUs. Concurrency by multiplexing the CPUs among the process and threads. The operating system is responsible for the following activities in connection with the process management: creating, deleting both the user and system processes. So process can be created and deleted. It doesn't mean that create a file or delete a file. When file is done and saved in a hard disk drive and it comes into memory, and therefore in CPU, is copied from your hard disk drive, right? Unless you override it back. So destroy means here is delete. Deleting means here is not the deleting of your stored file, but deleting from your memory or deleting from your CPU. That's it. Suspending and resuming the process. Why we need that is because we want to do in concurrent processing. Okay. Providing mechanisms for process synchronization. Synchronization and communication and deadlock handling, they're all handled by your operating systems. Lock mechanism is very, very important. Okay, locking. Why locking method? Locking method is needed. See here, I'm not sure you've had that experience while you are working on a computer. You open up 2 files, and same files 2 times. Sometimes it's possible, right? Same object running separately on your same computer. You touch this file and also touch another file, try to save, then your operating system complains. Hey, you have another processor is running. If you have 2 different versions of the same file available on your memory, then your operating system does not know which one needs to be persistent. So that you need to choose. How can you choose? You need to kill one process. Therefore, you need to have one file that should be saved. Why do we need to do that? Because we want to keep the consistency of a file. You don't want to have two different versions of a file at the same time. Then there is a big problem, right? When you collaborate with your friends, and two files finally came up. They are not really one version behind another. This has a brand new piece there. Another one has another brand new piece. Another. Then one cannot subsume another. You might have a problem. You need to do it manually. Okay? Therefore, we need to do lock. Locking process is this. If you want to change your file, then you need to gain the lock on this file. Whoever has that file can revise that file. If somebody does not have lock but wants to modify this file, it is not allowed. That is a locking mode. Reading is possible, reading. Okay? Multiple reading is always okay for consistent reasons. Million times read, still that is consistent because nothing changes, right? But at any moment one single bit is changed, then there is a new version. So anything that needs to be changed, then before it is changed, you need to gain the lock. Okay? But there may be the case that two programs, well, one single program, for example, one single programs, but opened twice. This guy tried to write, and another guy tried to write, but right now the lock is held by this guy because he is working on one piece of that file. The other guy has another type of lock, another piece of that files. Without completing the job, there is another mechanism, two-phase locking mechanism, which means if you acquire lock, then lock can be, there's increasing the mode. Once you release the lock, then there is a shrinking mode. But anyway, that type of mechanism developed. Therefore, there is a case of a deadlock, which means this guy waits this guy, another guy, which waits me to complete. I am waiting for you to complete, but you are waiting for me to complete. Then that is a deadlock, right? Both are waiting. Hey, you finish it first. No, I cannot finish it because I need something that you need to finish first. Both are talking about that. Then that is a deadlock. Deadlock needs to be handled by operating systems. If operating systems cannot do, then you have to do it manually. How? You can think in the real world situation. For example, if I arguing with Vishnu and, hey Vishnu, you have to finish this first because I have to do the second job here. Then Vishnu said, hey, I need for you to finish it. Therefore, he needs to do his own second job also. So we both are waiting. If you allow this, then this misuse the resources continually, never ending. In the real world, how can you handle it? Huh?
Okay, would you like new source, like third source, can help you
There's no way that you can resolve but kill one guy, right? No, that's a system issue, system terminology. So we can victimize. Victimize one process. Unless otherwise, both are waiting. Your system is hung, finally. So we victimize it. That is implemented also. Okay? Storage management. So let's skip this. Storage management. Operating system provides a uniform, logical view of information storages. So file systems, operating systems activities includes creating, deleting files, and primitives to manipulate files and directories, mapping files onto secondary storages, backup files, and everything, so that this function needs to make sure that once you store files, then those files should be persistent until you explicitly delete. Okay? There is a mass storage management also. Data grows, files grows, but for example, big data, then usually at the school level, even if we say big data, then it's not really big data, right? Are you really handling big data? No, we just call it big data. It's just data. If it is big data, then data cannot be available from one storage. How can your operating systems handle multiple storages? That is also here the issue. Okay. When you save your file, your operating system knows the free space, so that operating systems store your file on that space. And then your operating system needs to know where that file is located. Therefore, next time when you come back and click that file should be brought up. Otherwise, you don't rely on your operating systems, right? This should be consistently managed. Protection and security. Yeah, that is our issue, right? Protection and security. So each file has also some protection and security management. Windows operating systems does not have very strong mechanism, but Linux has, right? Linux has. Each file has the creator, owner. Each file has user groups, and each user group has a different execution mode. For example, this group can read my file, but cannot change. Vice versa. This guy can read, but cannot execute it. Those are all things, all the privileges can be set to each file that is possible in Linux operating systems. Database systems is much more than that. Right? For example, there's a role-based. You're the same person, but if you log in the database as a as a user, arbitrary user, then you can read data about yourself only. But if you are the manager, then you can read
all the information about your subordinates. Okay, that type of things can be defined. We call that access control. A lot sophisticated access control mechanisms have been invented and also implemented. Very nicely implemented since 10 years ago. See here, user ID, group ID. If you are working on Linux operating systems, then you have your own ID and you are in a certain group, so that there's privileges. As a user, you have certain privileges. As a group, you have certain privileges, and then there's a privilege escalation. If it is allowed, then you can have, for example, with normal privileges, you can read your file only. But if privilege is escalated, then you can modify your file, for example. Computing environment. We have now traditionally standalone and so many different levels of I want you to read. And then mobile, we have Apple iOS and Google Android. And smartphone and tablets. Okay. And also we have distributed. Not only in these ones, but we have also PAN, right? Body area network, for medical purpose. And also we have a client and server, but we implemented that in socket programming in our case. That is possible. Peer-to-peer. If you communicate only one-to-one, right? Your client to another client, you share. You open up your socket only between you and them, another guy. So you can access the other guys. He can also access me as a peer-to-peer. Virtualization, VMware. I think, yeah, this is a good slide. Without virtualization, this is the structure. You have a hardware. If you build operating systems, then operating systems has a kernel, and on top we have multiple processes, jobs available. Okay. But in virtualization, onto the same hardware, you can install virtual machine manager. Okay, so you have each different virtual machines, VM1, VM2, VM3. Each one of these will be the same as this, right? But this is so powerful because you have multiple different kernels available. Say here Windows 10, here Ubuntu, here OS 10, and multiple different. Cloud computing. we have, for example, software as a service, cloud computing, platform as service, cloud computing, and infrastructure as a service. Software as a service, cloud computing is, for example, you all have a Mercy Mavericks mailer, right? Mailer, that is Google cloud computing, software only, that we're subscribing. Or maybe some services, I mean a platform, I do not know exactly, but at least software as a service, but not the infrastructure as a services in our case. There's cloud computing, real-time embedded systems, real-time OS, that is that has been developed several decades ago. So real-time OS is really needed. Many microcontroller units, MCU, build that real-time OS and do continually 24/7. Open source operating systems is available. So we do GNU Linux for BSD, Mac OS 10. If you have a Mac, then that is coming from Next. Operating systems. That is modified from BSD. This is a Berkeley software distributions, and it is improved at the CMU, Carnegie Mellon University, and it is adopted by Next, which is revised to Mac OS 10. Linux has a very different distributions available. CentOS, that is the operating systems our website is running on, and Ubuntu. Many of the courses use that Ubuntu also. Okay. The future computing power, in addition to this, is, as I explained it to you, that is that is called FMEC. F means fog computing. Mobile, edge, computing. Okay, so FMEC. Any question? Okay, what we will do in the second phase, we will do. Okay, to finish up operating systems, we need to do some stuff available on the text. Text is available here. If you click this operating systems in Python, then you will have this. Okay. Little bit of exercise available, so we'll do that here. Operating systems modules have been provided to Python so that you can work on it. What I'm going to do is to run Python user interactive mode. Then you can, if you want to do something about operating systems. I know you have operating systems command to change directory. Probably some students do not know. So let's start from there. Let me quit this. See, where are we right now? We are here in E drive. This is the directory. Directories. This is so-called the file system. File system is organized hierarchically. So at each level, on top level we have, for example, if I go to C drive, now I'm talking about Windows systems. If you are working on Linux or Mac OS, then a little different. If you have a Mac OS, then you can do this, CD and slash, then it'll go up to the top. In Windows, you can do CD and backslash, then it'll move up to the top. See here, in this path, I have I have only C drive, right? I mean C drive and E drive and things like that in the Windows systems. But in Linux and Mac OS has a little different file system mechanism. There, if you have different devices to attach it, then they mount it. And all such things are available in device directory, DED. But Windows systems is more clearly that you can see, for example, if I bring Windows browser, then you can quickly understand. Where are you? See here, if you click this PC, then in this PC you have C drive, D drive, E drive, H drive, I drive, N drives. So those are all. It's not really. Windows system is not really tree structure. Tree, if it is a tree, then there is only one root. Everything is a one hierarchy. But Windows system is a little different. We have so many tops. C drive has a top, D drive has a top, E drive has a top, and so on and so forth. So push this aside. Here in the C drive, for example, if you type dir, then you can have il, then you have multiple. See here, dir is a command, which is a program. This program is already loaded in main memory. Therefore, you can execute this dir program. Dir now is nothing but a process. So dir process takes argument /w. If I don't do that, simply dir, then there is detailed information about each directory. If I want to do dir and /w, w is wide display. Therefore, multiple directories are displayed in this way. So I have a multiple of those, right? And one log file. If you have anything in square bracket, then that is a directory or folder, in other words, so that that folder contains many other files as well. Okay, so this is the hierarchies in C drive, but I I have E drive also. So that is my E drives, right? I have John's backup. This is, if I go back to the top of that directory, that drive, then I can do CD backslash, then it is all the way up. There, if I do dir, then I have those subfolders: John's backup, process video, iOS apps, to be deleted soon, 555, and others, right? So if I want to change it to the low level, open up another folder John's backup, then I need to do CD for change directory, right? Then I can come in the John's backup, and then I can see the directory. Similar, those things can be done in Python. So I can open up Python program process. So C colon, then there is a C drive, where there is a Python 36 folder, which contains a Python process, Python file, Python executable file. That is a file that I want to execute it. If I hit enter here, this is a program, right? Hit enter here, then there's a user interactive mode. Now, I am not in OS. I am inside the application program, which is Python. In this Python program, can I ask my operating systems to do some operating system management? That's possible if we import OS. See here, import OS. So I can do import OS. Okay? And after that, this OS has, let me see if I have modules OS or help OS. Help. Oh. Help. OS. So OS routine that and OS has functions. So OS.path, OS.name, OS.current dir, parent dir, OS.sep is a path separator, OS.expsep is an extension separator, alt-sep. So many useful functions already developed, right? You simply use it. So I can do OS get CWD, which is what is the current working directory? Get C current, W working, D for directory. My current working directory is, this is a full path, right? I open up this Python user interactive process in this folder. So it gives me that. You can change the directory. So os.chdil, and then you can change it. For example, I want to change this. Currently, that is John's backup. Let me see. Get dir. Do I have that? Where's that? Instead of guessing, so we need to take a look some of the things here. get CWD, get CHDIL, change directory, get login, get process ID, get file directory open, close, file change mode, change owner. This change mode and change owner, those are available in Linux operating systems. All of these functions are available in all operating systems? No, it's not, right? Some of the functions are available or are not available in some operating systems. Some are available in Windows systems, some are available in Linux. List dir, that works for example, os.list dir, then I can list up all the files in that, what is the current directory? Here, from there, right? So if I want to change into Mercy or research, let's do Mercy. Then os.change dir, and then I can put Mercy. And then I can see also get CWD. Then right now I am at Mercy. Here also I can see os.list dir. Then I can see the list of all, not all, but top of the first level of first level under Mercy directory. We can make directory. We can open, read it. If you want to have files, then you can open and read, remove directory, send the files, stat, write, start the file, systems, random number generator. Those are possible. So one example that you could do is this. I want you to do, there is also system files, system modules, and OS modules. System is more related with your programming. For example, those who knows Java, if you want to print out something, then always you need to do is system.out.println, right? That is the thing. System, sys can be imported, and then if we want to deal with the OS command, then OS together. So when you have sys, then you can have some arguments from the system. That is this. Okay. So for example, if I can do here, then open import sys, and then you can do actually sysarg yeah, we need to send something from outside, so it's not really needed here. So what we need to do is to do, let me get out here, and then let me change it to this. So notepad OS test.py. You want to create new file? Yes, I want to create new file. Oops. And here I can do import sys and import OS, and then as a practice, we can print the host of operating system is, and then you can say name of that operating system, as we did here, right? And then if you do sys argv, then as you execute that your Python program, you can enter the arguments, external arguments, together with your execution command. That arguments can be taken by your program. That is this: 1 colon and square bracket. Can anyone explain what this means? Argv returns a list, right? List. But you can access the list by index. If we put here 0, then you can, that tells you the command itself, the file itself. If you do 1, then it returns from the second argument, second element of the list. Okay? So what I want to work with you here is print. We can say what included with the file is sys.arg. Let's try this. And then we can save this. Oh, we already saved that, right? But we can redo one more time. os.py .py in Mercy 505 in class, save, yes. Okay, let me execute this file. How can I execute it? In command line, C Python 36 and Python, and then that file is OS text. Why I said OS text? OS text.py. If I enter this, the object is str object is not callable. So this is not really hold on. Let's try in this way. To verify it, you can do import OS and os.name. Oh, os.name is not available. What about str? print str os dot name string object is not callable. It's not. It's not the module. Okay. Maybe. Okay. That's. Okay. So I commented this out. os.name is not available. But sys.arguments is available. When I do this, os text.py, this is the file name. This is this Python file, right? I run this Python by calling a particular Python version of an interpreter. So this is a command. But when I do this, and then I can put here 1, 2, 3, 4, 5, 6, 7. See what happens. See here. What included with the file, colon. Previously, if I don't do anything, then os text.py. But in this case, I included more arguments together with that file name, number 1 to 7, so that they are all in one list. os text.py 1, 2, 3, 4, 5, 6, 7, and close. Okay? You guys following? Okay. So let's, by knowing this, we can continue to work for this for loop. So dir is c in sys.argv 1 colon. If we do 1 colon, what does that mean? If I don't do anything, then it returns everything together with this file itself, right? In one list. But if I do here using index 1 colon to the end from the second element, right? So it excludes the code itself. Exclude the code, but whatever additional arguments can be displayed. That's what this guy would do. So if you enter multiple, then one at a time, right? So I have a for loop. So files os.listdir. If it is the dir directory, I said os list dir of that directory, and then print files that's it. So if you run this, I cannot run. I want to run, say, if I have any directories. I do not have any directories. But what I can do is I can make a directory, mkdir, and then test directory. Okay. And then I want to copy dir m colon.py. How many files? Oh, I have many m's. So what I can do is I want to copy any files starting with the m and then extension py to what's the directory? Test directory. Okay, so if I do test, then I have those 5 files. How many files? 7 files, right? Okay. Perfect, fine. So I want to do, what I'm going to do, instead of 1, 2, 3, 4, 5, 7, I want to do here test, which means directory name is entered. In this directory, in this directory, I have another subdirectory called the test. So I want to enter this directory as an argument to this program. Then this program takes that argument, whatever one after that, and then print a file. See what happens. That's it. So when I do this, the first thing is that what is the arguments entire? So itself, and then subdirectory. And then that subdirectory is a list, so that for each, I give you only one subdirectory, test, right? So in that test, to see if any files, that is the files, right? So I print that files. How many files? I have these files. So these files written here. Say mybubble.py, 1, 2, 3, 4, 5, 6, 7. This is what it is. Okay? So if you read this textbook, then I explained a little more. So there is we do not have enough time right now, but next project that I want you to do is something about this recursive execution. What's this? So exercise is that as an extension of example 4.3.4, write a Python match py to visit all the subdirectories of that. Right. I think this is. So what I want you to do is that I want you to practice this program. What this program wants you to do is that you need to read argument parse manual, then together with your program itself, you can have some options by -e or -- minus dash 2 minus and ext. Then you can put their extension and another arguments, and then some works. So what I can give you an example is, if I can go to oops. OS and this is what I want you to do. This is the extension of that program that I that you can see here. You can practice this and get some learn, and then do this. If I do this, for example, C:/Python 36 Python, and then dir scan recurse match py, and then you can do extension is any Python program and then another option that you can do is keyword equals print, and then you could do that from here to that. Okay, so Control C and Control V. Okay, see what happens. So what I want to do is that this program takes this directory /John backup mercy 505 from directory one above. But we can specify any directory. But in this directory we have multiple Python programs. So extension of Python is star.py. Okay? I open up each file. Each file has print statements, so that I want to display that print statements. Keyword that I want to find from any files, any Python files, if there is a print statements. That's what I want to match. This kind of things cannot be done in simple Windows programs, right? But if you have Linux and Unix programs, then you could do this more efficiently. But in Windows, you can do this in Python. Oh, something missing, right? What's the keyword? Unrecognized. Keyword is not recognized. So word is -k. Okay, that's true. We can simply do -k. Okay. So it runs. It open up all the Python files. Okay, listen. All the Python files open up and read that Python's source code. If there is any print statements, it displays. See here, in this file, I have these print statements, and all print statements are printed. In another file, for example, OS directory 1.py, I have print statements that interrupt kby.py, I have a print statement, print try. See, all of this. What is the benefit of this Python programs for the Windows systems? Windows systems itself, if you want to find some keyword from some files, but you forgot the file name, you do not know where it is, but you know for sure, oh, I put that word. Then what do you need to do? Usually, you open up all the files to see if it contains that ones, right? It takes so long, and maybe if you are not lucky, you cannot find it. but these simple programs can find it all. Right? This is the beauty of Python programs. Python programs, particularly to operating systems. So last week we did the Python programs for networks. Here it's operating systems. So this is your homework assignments. This is it for today. I'll see you next week.